So thanks so much to everybody for joining. I guess has the live stream started? If not, we can start it now.
Yes, ma'am, we are online. Yeah.
Okay, great. All right, perfect. So I'm just curious, those of you who have joined, is everybody planning to give the exam this weekend? Could you just raise your hand if you're planning to do that? Okay, Sanjay is. What about the rest of you? Okay. All right. Cool. That's interesting. This was more of a like I'm a last minute person, so I figured that it may be helpful for some of you to do like a quick last minute revision sort of thing, from the point of view of the fact that the exams. But yeah, if you're not giving the exam, I guess this doesn't hurt anyways. But yeah, if you have any other questions related to the course, etc., definitely let me know. Could you give me a +1 in the chat if you can like see my screen and. Like, do you see some grid paper? Okay. All right, perfect. Thanks. Okay, great. So first off, I think I also want to apologize a little bit for like the timeline with the last couple of weeks. So I think we realized as we were going on and from the feedback that maybe we overestimated what can be done in 12 weeks a little bit. So we decided to kind of keep the core of it within the first 11 weeks. You might see that like the introductory part of week 12 has been released, and I think just like to tell you a little bit about reductions, because that's probably something you haven't had a chance to look at properly during the run of the course itself. So I'll talk a little bit about that today, just drawing your attention to, I think, the most important aspects. Um, excuse me. And also, since you have completed the course more or less by now, I also want to tell you a little bit about where you can go from here and what are the opportunities, what are the next courses that you may want to do and things like that. And if anyone's interested, or my default plan was to do like a quick recap of like just the main highlights from all the weeks that we have seen so far, just trying to pull things together a little bit. So that was kind of the plan. But once again, if anybody has a specific question, I'm happy to take that first and go over it. Okay, so I guess we'll go in kind of this reverse order of the agenda. Excuse me. So the first thing is you've just finished a course in parameterized algorithms, what we think of as an introductory course, but I think we've still covered a fair amount of ground. You might be interested in learning even more about parameterized algorithms. So there's plenty more to look at. I think this definitely covers a lot of the foundational material, but even this book on which the course is based was written back in 2015, and this is a very fast moving area. So a lot of developments have happened since. Many of the problems which were stated as major open problems in the book have since been resolved, and new ideas and new techniques have come in. But still, I would say that, you are well positioned right now if you wanted to read a paper in parameterized algorithms, if you wanted to work on a problem and use this parameterized perspective as an approach to solve a problem. I think you're in a good position to do that already. But there are a few courses. There's a course on advanced parameterized algorithms that's run by Saket, which you can find on YouTube. And more generally, I think looking up courses in other sort of modern algorithmic frameworks, like whether it's dynamic or streaming or approximation, which has of course been around for a while and is constantly getting new innovation coming in, I think empowers you to really work on the frontiers, because a lot of interesting work is happening, for example, in say Fbt approximation. You've learned so much about kernelization. It turns out that not every problem has a nice kernel. We've seen positive examples. We haven't really talked about the limitations of the kernelization framework. So it turns out that there are many problems that are Fbt that don't have polynomial kernels. So it's the next best thing you can do is that you can try to come up with some approximate notion of kernelization. And it turns out that many people try to come up with what would be a natural concept of approximate kernelization, and none of them really stuck, in the sense that either the definitions were limited, you can come up with a definition, but if you cannot apply it to a lot of problems, then the definition doesn't catch on, right? And then not as many people use it, and then it kind of fizzles out in the literature. So after multiple, I would say, false starts, I guess there was a recent paper called Lossy Colonelization. This one seems to be like one that's really captured in a reasonable way what you would want to think of as approximate colonization. So it's a fairly sophisticated definition. And it turns out that, it's a very widely applicable framework. And if you look up lossy kernels, it's a fairly recent development. So lots is still being explored. I think there's a lot of potential for trying to come up with lossy kernels. And for reasons that will become clear if you were to look up the definition, this is interesting even for problems that already have polynomial kernels. Coming up with FBT approximation is interesting even for problems which are already in FBT, because maybe you can, so let's say you have a really bad FBT algorithm, like the running time is, expensive. What if you're willing to let go of the exactness requirement and you say, okay, I'm willing to live with an approximate solution as long as it's a good approximation, but if you save me a lot of time, that's a trade-off I'm willing to make, right? So there are lots and lots of trade-offs that you can explore. And excuse me, having a little bit of background in approximation algorithms helps you be inspired to sort of, apply those techniques alongside whatever we have seen in the FBT context as well. So FBT and approximation is definitely a big sort of emerging area in algorithm design. And I would say this course definitely does a lot of the groundwork from the parameterized side. If you already have exposure to approximation algorithms, then this is definitely something to dig deeper into. And if you don't, then I think this would be a great way to, or a great reason to get acquainted with approximation algorithms. So both for FBT and kernels, I think these are very interesting things to do. And the other thing that we haven't explored is fine-grained notions of hardness. So most of our focus has been on taking things that are NP-complete, NP-hard, and trying to come up with interesting parameterizations that are hopefully relevant in practice. And then designing FBT algorithms has really had a very unilateral focus on that. But it turns out that just because you've picked up your favorite NP-complete problem and you've identified a parameter you like, it doesn't mean that you automatically can come up with an FBT algorithm. Like, just based on what you know about NP-completeness, you already know that if you take problems like, say, K coloring, for instance, and you try to parameterize this by K, then that's not going to be interesting, because even when K is equal to 3, we know that this problem is NP-complete, right? So if you come up with a f of K poly-n algorithm for such a problem, then you're in trouble with the P versus NP hypothesis, right? Because f of a constant, no matter how crazy your function is, as long as it's computable, f of a constant is still going to be some constant overhead on polynomial in n. So this is going to contradict our assumption, our well-loved, well-believed assumption that P is different from NP, right? This would give you a polynomial time algorithm for 3 coloring. So it is widely believed that, K coloring, in fact, does not even have a XP algorithm, forget FBT, because the same logic applies even if you come up with something like n to the GK, for instance. So even a XP running time is kind of ruled out, and all you need to rule this out is just the classical framework, right? So you just need to assume that P not equals NP for you to be able to draw these conclusions. On the other hand, what if I want to say that, for instance, clique does not have a FBT algorithm parameterized by solution size, or independent set does not have a FBT algorithm parameterized by solution size? Why would you believe that even? Well, I mean, there are lots of reasons, some of them a little more technical than others, but for now, let me just go with the fact that we haven't been able to design FBT algorithms for these problems. So can the assumption of P not equal to NP take us to a conclusion where we can say that, okay, if P not equals NP, then then it is also true that clique is not an FBT, for instance. So as of now, we don't quite know how to say that. But if you think about what this assumption is really telling you, P different from NP, what it's really telling you is that SAT, or you can pick your favorite NP complete problem. Let me pick 3SAT. You're going to say that 3SAT has no polynomial time algorithm. Now, if you strengthen this assumption a little bit, you say a little bit more. So I want to say that, okay, forget polynomial time. 3SAT, even if I give you more time, you still cannot do it, right? So you know that 3SAT can be solved, for instance, in 2 to the n time. You can simply try all possible binary, like these are Boolean variables, right? So you assign them true or false. So you have n variables. And just try experimenting with all possible ways of setting them to true or false. That'll take you 2 to the n time. So I want to say that, okay, that's something that you can do, but anything better is not going to work. Anything better in the following sense. So I want to say that 3SAT has no 2 to the little o of n plus m algorithm, where m is the number of clauses, n is the number of variables. So notice that this is a stronger assumption than the first one, because of course, if you don't have this sort of an algorithm, which is an algorithm which has way more resources, then of course you will also not have an algorithm which is only allowed far less resources. But it's possible that you don't have a polynomial time algorithm, but you still have a sub-exponential algorithm. That's conceivable. It's definitely not implied by P not equals NP that there is no sub-exponential time algorithm. So because it's not implied by that, this has its own name. This assumption is called the exponential time hypothesis, and it's reasonably widely believed. Maybe there are some people who believe P is different from NP, but they don't believe the ETH. But I think a lot of people believe both, actually. You only need to believe ETH, the other one is implied. There is an even stronger version of this hypothesis, which tells you, which is slightly different in the sense that it says that SAT cannot be solved in like even 2 minus epsilon to the n. Like you can't even improve the base of the exponent for SAT. That's called the strong exponential time hypothesis. And it's a good exercise to show that the strong hypothesis is indeed stronger. It's a stronger assumption. It implies the exponential time hypothesis. So all of these stronger assumptions let you actually prove more fine-grained hardness results, right? So now you can actually say that, well, clique, it turns out if you believe the ETH, and this is something we do plan to add at some point to the course. So if you believe the ETH, for clique, you know that there's an n to the k algorithm, which is just, try all k-size subsets of the vertex set. If any of them is a clique, then report it, otherwise not. So going over these subsets and checking if it's a clique is like a polynomial overhead over n choose k, and you know that n choose k is roughly n to the k. So if you believe the exponential time hypothesis, you can actually show that you cannot expect an n to the little of k algorithm for clique. So anything that's sub-exponential in this sense would not work. Because if you had such an algorithm, you could use this algorithm to come up with an algorithm which is sub-exponential for, I think the reduction is from 3 coloring, but you can reduce 3SAT to 3 coloring. So chaining everything up, you know that clique is actually, so this of course also tells you that you cannot have a FBT algorithm, because that's much stronger in terms of the demands and the time. So this actually shows you even more. It says that you cannot even expect a sub-exponential XP algorithm for clique, right? So, and similarly, like you've seen a lot of algorithms with respect to tree width and tree decompositions. So for even problems like vertex cover, you have, for instance, 2 to the tree width. And you might wonder, can I make this 1.7 to the tree width? Right? Because this algorithm here, the exponential algorithm in tree width, it's more or less what you might call a trivial algorithm. Like once you have set up the definitions and everything, what you're really doing here is pretty much brute force, right? The DP table is basically saying, look at all possible ways in which the solution can intercept the current bag. So you're really looking at all possibilities, and there's no there's no optimization at that level. So sometimes it's interesting when it turns out that the obvious thing to do or the trivial thing to do is actually the best that you can hope for. And that's what happens with a lot of these tree-width-based algorithms and others as well. So for this, you need the strong exponential hypothesis to be able to say that you really cannot improve this to anything better. And the way you would use again, these hypotheses is by the framework of reductions. So yeah, while I'm telling you about this, this bucket list of things to do next, let me also tell you a little bit about reductions. And anyone who is doing the exam tomorrow, this is really all you need to know about reductions, more or less. There's nothing else that's going to come up really. We decided to omit questions that depended on reductions by and large, because the material is something that we decided to hold off on, but it's useful to know the following. So in general, if you have a problem, so in general, if you have two problems, A and B, and you manage to reduce A to B, what does that mean? It means that you have this is the same reductions that you know from the story of NP-completeness, by the way. So you know that there is some algorithm, let me not use F because it's overloaded. Let me just say that you have some procedure P, which can take X, because now let's say we are going between parameterized instances. So let's say that this guy takes an instance of A and it produces something which, let me call this X prime K prime, and this is an instance of B. So in a normal reduction, what do you want? What you want is that if you can reduce from A to B, right? If you have, this is the sort of thing that you hope to get out of a reduction. What you hope to get is the following. So if B has an algorithm, an efficient algorithm, and A reduces to B, this implies that A also has an efficient algorithm. This is what you want to be able to say, and this is why reductions are useful in the first place, right? So if you've done, for example, if you've learned max flow, so many problems reduce to max flow, right? And why do we do that? It's because we have a very good understanding of max flow. We have nice algorithms for the problem. So if you can take a problem and you can convert it into an equivalent instance of max flow, then you can just run the max flow algorithm and you have solved your problem with no effort specific to the problem other than coming up with a mechanism of transforming it into an instance of max flow, right? So if you take an unknown problem, something that you're working with, and you reduce it to an easy problem, then this is helpful because it helps you solve your problem, right? How would you solve your problem? You would perform the reduction, you would get an instance of the easy problem, and then you would run the algorithm that you know for the easy problem. Because it's an easy problem, it has an algorithm, and you would run that, and that's how you would solve an instance of X, right? So let me say to solve X, in general, this is what you would do. Reduce of X. So this is an instance of the easy problem, and the easy problem probably has some algorithm. So you'll run that algorithm on the reduced instance, and that's what you will return as your answer, right? And for this whole thing to work, right, you need a couple of things. The first thing you need is that this reduction procedure that you have come up with should be efficient, because otherwise this whole process will not be efficient, right? So if your reduction itself needs, say, exponential time, then this is no fun, right? This overall process will simply not work in polynomial time if this reduction step itself is expensive. So you definitely need the reduction step to run efficiently. So in the parameterized setting, that would mean it runs in polynomial time. And then, of course, you're assuming that you know how to solve the reduced instances efficiently, because we are saying well, this is an easy problem. So, so by definition of easy, whatever that means in the parameterized world, easy may mean FPT. So this algorithm here will also run quickly because of this promise that you've reduced to an easy problem. So combined, everything will run quickly if the reduction runs quickly. But for correctness, what do you need? You need that this answer that you're returning should be meaningful. It should be the right answer. And that will happen provided you maintain equivalence. So every yes instance of the source problem should be mapped by the reduction to a yes instance of the target problem. Every no instance of the source problem should be mapped to a no instance of the target problem. So this is what we call equivalence. And you've seen this for NP completeness reductions. This is what you do. This is where you spend most of your effort, right, in showing that the instances are equivalent. So for Fbt reductions, it's no different, really. You still want that the instance that is spewed out by the reduction is an equivalent instance. The thing to be careful about is really the running time. I mean, of course, you want your reduction to run efficiently. So the reduction should run in Fbt time. But you also want that the parameter of the new instance is bounded as a function of the parameter of the old instance. Because if this is not the case, when you run the Fbt algorithm for the reduced instance, you will get into trouble. It'll not be a Fbt algorithm for the original instance. So that's going to be difficult. That's why, for instance, you might say independent set reduces to vertex cover. So independent set is G comma K, vertex cover is G comma N minus K. So what do you think? Can you run the Fbt algorithm for vertex cover to get an Fbt algorithm for independent set? Notice that this is a perfectly valid reduction, right? It's the same graph. So G has a independent set of size K if and only if G has a vertex cover of size N minus K. That just follows from the definitions of these two quantities. But would this make sense to propose as a reduction, right? I mean, you can always define it as a valid reduction, but will you get this consequence that you want, that if vertex cover is Fbt, independent set is Fbt? Will that happen here? So does anybody want to sort of commit to whether this makes sense or not? Like, let me know in the chat or feel free to unmute yourselves. Okay, so okay, let me just say that this will not be a valid reduction in the sense of what you want out of a reduction, right? So if you transform independent set to vertex cover in this way, and you run the algorithm for vertex cover, right, it's going to take time 2 to the n minus k, and it will run and it'll give you the right answer. But the time that it takes is clearly not Fbt in the original parameter, right? Because you also have an n and a k and it's all mixed up and it's messy. Okay, so in a parameterized reduction, what's important is that the parameter should be preserved. So k prime should not look like something that's a mix of n and k, should be a pure function of k, and that is kind of crucial for the running time. And the equivalence is crucial for the correctness. So these are the two things that you want out of a parameterized reduction. And now what we have seen is that if you take your unknown problem and reduce it to something in Fbt, then you get an Fbt algorithm for your problem with this definition. What this also means is that if you take some problem like clique, which you believe is not an Fbt because of ETH, and you reduce this to your unknown problem, then that means that your unknown problem is as hard as okay, because of exactly what we just said, right? If you can come up with such a reduction and somebody comes up with a Fbt algorithm for X, Then this reduction combined with the other half of the jigsaw puzzle, which is FBT algorithm for X. When you combine these two ingredients, you end up getting a FBT algorithm for clique. How will that algorithm work? You will say, okay, let me take clique and reduce it to X via this reduction. Then let me run the algorithm for X, which somebody has come up with. And let me report the answer reported by that algorithm. And then I'm done, right? And this will be the right answer for clique because of the equivalence promised by the reduction. It will run an FBT time because a valid parameterized reduction is parameter preserving and runs an FBT time. So it's a valid FBT algorithm for clique, but then that is something that would violate the exponential time hypothesis. Therefore, you can conclude that X is in the same sort of category or status as clique in terms of parameterized intractability. So that's the overall framework. The main thing to remember is that you either reduce from a hard problem, from a problem that's known to be unlikely to admit efficient algorithms, or you reduce to an easy problem. There is no point in reducing from an easy problem or reducing to a hard problem. Both of these will not give you any mileage. Okay, you can come up with such reductions, but they will not be useful typically. Okay, so that's the main thing to remember with reductions. And then going back to what I was saying about next steps, well, when you come to reductions based on the exponential time hypothesis or the strong exponential time hypothesis, you not only have to be careful about the parameter being preserved, you have to also ensure that the parameter transforms only either as a linear function of the original parameter or just has a, like your new k should be the old k plus some constant. Like that's the only leeway that you have. And you'll start getting a feel for these constraints after you work with examples of such reductions. And it's totally worth learning a few of these examples because you really get these remarkable hardness results as a result of being able to do such reductions. So in particular, you can start saying more fine-grained things about what kind of algorithms are possible and what isn't, right? So you're constantly closing the gap between upper bounds and lower bounds. So most of this course is focused entirely on upper bounds, right? We have been trying to come up with better and better algorithms. We've been borderline obsessive about that. But on the other hand, there's this whole other side to the story where you're trying to say, okay, this is it. You cannot do better than this because you've really reached the limits of what is possible to do with these resources. And the way you show that is using the framework of reductions and coming up with the appropriate starting point. So if you believe the ETH or the SATH, or you believe you believe that P naught equals NP, whatever you believe, starting from that, what can you show? And you don't really have to believe in a particular hypothesis. You can just think of this as, okay, if I come up with a FBT algorithm with this problem, then the ETH would be violated and we will have efficient algorithms for SAT. That's a factual statement. And the weight of that implication will weigh heavily on some people's minds, and for some people it will just be like, okay, if this happens then that happens, so cool, let's try to make this happen, right? So some people will actually want to use reductions in the hope of some people may want to actually prove that some of these problems are an FBT to be able to maybe violate the ETH. Other people will say, okay, we believe the ETH, so we believe it's a waste of time to look for FBT algorithms for these problems. So this is one major thing that we've really omitted in the course, right? We haven't talked about hardness so much at all. And in fact, there's also a very exciting hardness story for kernels. I mentioned in passing while talking about lossy kernels that there are FBT problems that don't have polynomial kernels. And that's, again, something that involves making some interesting bridges with the classical world and, again, a different set of assumptions. But again, some very widely believed assumptions in general. This has something to do with the so-called polynomial hierarchy, if you're familiar with that. Some problems having a polynomial kernel would lead to eventually the collapse of the polynomial hierarchy, which sounds like a bad thing and something that you wouldn't expect to happen. And that's the situation right now. And there's, again, a whole framework for being able to show, again, largely based on reductions, but also some other techniques for showing that certain problems don't have polykernels. So these are kind of some of the topics. So ETH and SEP and hardness of polykernels. These are things that we're not covering in the ambit of this course. The focus has been more on just introducing you to the fact that there are hard problems out there and giving you some examples of reduction. So if you have some time, you could look at the week 12 lectures that are there so far. We may be able to add some more examples in due course for a future run of the course, but for now, whatever is there should just give you a taste of what kind of what kind of things people look at when they're talking about the limit of efficient computation in the parameterized world. Okay. Okay, so UGC and Gaap ETH assumptions, there's a question in the chat about that. Yeah, these are, again, another class of assumptions that are more relevant to approximation algorithms, I guess. So I'm not super familiar with, I should admit upfront that I wouldn't know how to either describe the intuition behind these assumptions off the top of my head or even I'm not even sure that I can state them very accurately, but what I will say very, very vaguely, and I'm sorry, this is not doing justice to your question at all, but what I am happy to do is if you could drop your email in the chat. I think there was a really nice TCS Plus talk about the UGC. And I remember really liking it when I saw it. So I could send you a link to that, and you could probably look that up. I think it's a really nice introduction to how the conjecture came about. But yeah, in general, I think these are the kind of assumptions that you have to head towards if you're interested in showing. So when you know that something is not likely to be FPT, you start asking yourself if you can say that, okay, in FPT time, can I get an approximate solution? And maybe you can. But then again, the next natural question is maybe even that is not possible. So how do you show that even an approximate FPT algorithm is not possible for a problem? So that will require, again, I wouldn't say upgrading your assumptions necessarily, but yeah, you would have to start looking at at least a different set of assumptions, right? And in general, what I will say about reductions in the context of approximations is that it's the overall same framework. You want to go from a problem that is hard to your problem to establish the hardness of your problem. But now the way you have to do it is, okay, again, the way I think it's useful to think about reductions is what is it that you want to prove, right? What's the theorem you want to prove? You want to say if A reduces to B and B has an approximation algorithm of a certain kind, then A has an approximation algorithm of a certain other kind, which is widely believed to be not possible, right? So let's say that we believe that vertex cover does not have C approximation for C less than 2. If you believe that and you want to use this assumption to show that, problem X does not have a C approximation for C less than, 5 or something. So really think about how do you want the reduction to go? A better than 5 approximation algorithm for your problem should imply a better than 2 approximation algorithm for the vertex cover problem. So how should the instances translate so that this happens? So this will motivate the definition of whether it's a gap preserving reduction or whatever. And I think the other thing to look out for is the PCP theorem in the context of approximation reductions that show hardness of approximation. So yeah, this is something that I will not say more about because I'm not sure that I'll really be able to say the right things off the top of my head. But as I said, let me even see if I can find the talk that I was talking about here, which may be interesting to look at. So. I think it was a talk even by Subhash Khote. Okay, I'm not like 100% sure because the description does not seem to have the details, but I think that's the talk that I was referring to. It's from a while ago, but I think you might. Yeah, I think this has like, this is in the context of some CSP problems, but nevertheless should give you some feel for what's going on here. Yeah. Yeah, in fact, I think some of the stuff mentioned here in the context of SAT and CSP is also interesting and relevant to the broader parameterized context as well. So yeah, if you can take a look, and I hope that helps. Right. So here we go. Okay. So in terms of, okay, just going back to things that we haven't covered, I think even in terms of algorithmic techniques, there are a few things that that we have chosen to omit, particularly in kernelization. I think we only had so much time. So there's a whole book on kernelization. From which I think we have borrowed a few, a few lectures here and there, but there's so much more to kernelization overall. And I don't just mean lossy kernels or hardness of kernels, just like pure, techniques for coming up with polynomial kernels. There's like a whole lot more to sort of do and learn. So, so that's something that you can, I think the book on kernelization definitely has, would be a good next step if you're intrigued by kernels. And in general, if you want to follow what's going on in the FBT world, I definitely recommend the FBT wiki. I hope that we have mentioned this in some of the lectures. So they have a section which is updated very, very regularly. It's the section on FBT papers. So you can, if you want to look at some of the recent papers that have just come about, definitely go into the sections which say FBT papers and conferences and FBT papers online. It's really very, very meticulously maintained. And, I think it's a great resource. It's a good place to just get a sense of what's going on. And also, if you want to find things to read, find things to work on, then that's, that this is a good place to get some updates from. Also, if you're interested in actually working on something, I think the best way to do it, I mean, of course, a great way to do it is to just get started and, be able to find relevant papers. Maybe there's a problem you're already interested in working on, or you're looking for a problem. It's certainly possible to do it by yourself, but typically such projects are also more fun when you do it along with other people. So as most of you know, and hopefully most of you are already a part of the Discord community that has been set up for this course, but you're welcome to reach out to either me or Saket. We're tentatively planning to do sort of a workshop, which is just more hands-on and research oriented sometime in December. So the plan is to just work with folks who are interested and available around that time. So it would be fun to do that. So just drop either of us an email if that's something that would interest you, and if December is a good time for you. And I'm sure like we'll keep letting you know if there are more things that we plan along these lines later as well. Along these lines, there's also ACM winter school in January, upper and lower bounds in algorithms. Let me see if I can find that for you. It's organized by people in CMI and IIT Madras, I believe. Let me. Okay, so the dates are 3rd to 12th January, and yeah, it's IIT Madras and CMI. I believe Akanksha Agarwal and Philip, I think, are organizing it. The website will be up soon. There's a bunch of winter schools happening, but this is the one that would be very closely related to the themes of this course. It says algorithms and lower bounds. So that's a combined announcement for everything, but you will find links to go ahead and register. I think it's a good idea to do that if you found some of the stuff interesting. It's, I guess, a 2 week, more or less a 2 week, like a 10-day kind of school. So that should be fun. Okay, so this covers, I think, whatever I wanted to say about reductions to the extent that we look at them in this course, and some ideas for things to do next, which mostly involve connections with whether it's approximation or looking more deeply into hardness and the limits of efficient parameterized computation and advanced techniques in kernelization. And of course, there's no end to advanced techniques in FBT algorithms. I think at some point you just have to start digging into papers to get a sense of, what's current. But yeah, I mean, hopefully this, the material that we covered in the course gets you to a point where you can comfortably read papers and take those next steps. Okay. I believe as far as logistics go, I think this course may be rerun again next year. Not necessarily next semester, but the videos will be available, and we will try and see if we can make notes available as well. We have been sort of just trying to read through them and edit them for clarity, and that's partly why it's taken some time. But I think we'll try and see if we can at least make the slides and the running notes available. So this will remain available from the course website for for good, so you can continue taking a look at it whenever you like. Okay, so that's yeah, so I think that's more or less what I wanted to talk about. As I said, I'm happy to do a high level recap, but I see that I've already blabbered for a bit too long, and we have about 15 minutes to the hour here. So what I would say instead is, if you have any questions from any specific topics that was or if you have any questions that are more general, feel free to drop them in the chat, and I'll try to see if I can address them at least partially. And or if not, I'll be happy to come back to you over time. But if there's anything specific, then please do let me know. Also, I really appreciate all of you joining on what's a fairly short notice. I think I just wanted to also have this opportunity to say thank you for sticking around till, all the way till the end of the course. I think it was great fun putting this together, and I hope that you also enjoyed it as much as we did in terms of creating it. Also, I believe all the assignment solutions have been released. So at least all the graded assignments. So let us know if any of the content in those solutions don't make sense. I think there were a couple of questions. There's one about balance separators where I think the correct option was not marked correctly. That has been corrected. And there was one question, I don't remember from which assignment, that had a typo in the options, because of which there were no correct answers. So that's been removed from the grading process. So I don't really recall anything else in terms of logistics. And, if all of a sudden they started asking several quarterly reports, and we will send you, depending on how much money you have spent, what you have done, the next quarter's, how much money you will depend on how much you have spent in the previous quarter, and so on and so forth. So types keep coming up with what is called budget control, what is called expenditure management, the bucks. And this all right, so I don't see any questions in the chat, and I'm not sure if anyone's tuned in on YouTube, but I think it's safe to say that we are good as far as questions go. And I'm just trying to see if I missed anything in terms of logistics, but I think not. Yeah, I mean, I guess, one thing that I was hoping that I could do is maybe like give you concrete pointers to playlists of courses that you could take from here. As I said, there's definitely one on advanced parameterized algorithms on the Math Science channel. There's one shorter playlist which has like about 10 videos, but I think there's a more recent version of that that's somehow more structured and even more contemporary. So it's just trying to see if I could quickly find the right version, but I don't have it handy right now. What I will do is maybe roll up these links into an announcement and send them over an email soon so that you have some ideas for next steps. But as I said, please keep in touch. And if there's any interest in, catching up in December or anything like this, please let us know. If you are interested in algorithms broadly, do sign up for the winter school. I think looked at some of the preparation and I think it's super exciting and totally worth worth attending or helping out with. If that's something that you think you can spare some time for, get in touch with the organizers. So yeah, I guess that's pretty much all that I had to say. Once again, thanks a lot for joining in on a short notice, and more broadly, thanks for taking up the journey of this course with us. Really appreciate it. And yeah, we'll look forward to being in touch and see you all soon, I guess. We can wind this down here and call it a day. To anyone who might be writing the exams, I think there's at least one of you. All the best. And, once again, feel free to write in if you had any doubts or questions from the exam itself. So thanks a bunch. Take care. And we'll talk soon. Thanks so much, Tanmay, Satyabrata. We'll look forward to keeping in touch. Yeah, it's great to have all of you. Saurabh as well.